Welcome back. I have another gravity dam exercise here. Again, it's made of concrete and it's symmetric about the vertical axis. So it's symmetric about this axis here. The density of the concrete is 2.5 megagrams per cube meter. The density of water is 1 megagram per cube meter. Now this dam has a width, and this width is 8 meters. And again, just like last time, your task is to find the smallest distance d that would still prevent the dam from tipping over about point A. So considering the depth of the water, which is 9 meters, what is the minimum distance d that still keeps the dam in place? So that's your first task. What's the d minimum? And then once you have it, then you also need to find the center of gravity of this entire cross section. Of course, you can do it through integration, but as a hint, there is an easier way. You can divide this cross section into 3 parts, 1 rectangular part and 2 triangular parts, and that's the end of the hint. Try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. Let's now find the minimum distance for d meters with which the dam will not tip over about point A. This problem can be solved in a similar way like the previous dam exercise. The only difference now is that the shape of the dam is different. The magnitude of the load distribution increases with depth linearly, and it's normal to the surface of the dam. Here in this point, the force distribution per unit length is 0 newtons per meter, because your z here is 0 meters, and then here at point B, your WB equals pressure times 8 meters, which is the width of the dam. So you go from pascals to newtons over meter, and so you have 1000 times 8 times G times Z, and Z is 9 meters. So in the end you have 72,000 times G newtons over meter. That's the length of this arrow here, the final arrow. That's your WB here. Let's also calculate the length of this side of the dam, the one that is exposed to the water. Let's call it L, and we can find L using Pythagoras' theorem. You can see that we have a right triangle here. You have this side, the horizontal side, d minus 1.5 over 2, and then you have the vertical side, which is 9 meters. So in the end you will have 9 squared and the other side squared, and all that you put under square root. That's the length of this side here. And now I'm going to take this side that is exposed to the water, and I'm just going to draw it horizontally. So the total length of it is L. That's this one. This is your rectangular pressure distribution. So this point here is B. And remember, this one here, that's your WB, which is this one here. From the previous videos, we know where the center of pressure of this force distribution is. It's right here, this point. And it's 1/3 of L. The total force due to this pressure distribution is L times, and now your WB, which is 72,000 times G, divided by 2 newtons. And it acts through this center of pressure here. So if I draw this dam here again, then the center of pressure, CP, is this distance here. And now this force, it acts through it like this. Then we can say that you have an angle alpha here that we can use to decompose our force into its x and y dimensions. And so you have 90 degrees here, and you also have 90 degrees here. If I say that this angle is 5, then due to geometry, because this force is perpendicular to the dam's wall, also this angle here is phi, which means that this angle alpha here is also this angle alpha here. So you see, we are dividing our cross-section into 2 right triangles and 1 rectangle. And using the geometry of one of the right triangles, we can now find this angle alpha, which will be the same angle like here. So if this force here is F, then Fx would be F times cosine alpha, and Fy would be minus F times sine alpha. You have a minus sign here because the vertical component points down. And now what we are going to do, we're going to find cosine alpha and sine alpha using this right triangle here. You know that the vertical side is 9 meters and the horizontal side is this one here, d minus 1.5 over 2. And you know that this is your angle alpha. And you also know that your hypotenuse is L, which is this one here. So right away you can say that cosine alpha equals 9 over L meters and sine alpha equals d minus 1.5 over 2 divided by L. It makes sense, right? In case of cosine, from your angle alpha, you take the adjacent side and you divide it by the length of this hypotenuse L. And with sine alpha, you take the opposite side and you divide it by L. And now, this force here, due to this force distribution, is the force that would cause the dam to tip over about point A. However, notice something interesting. Since the pressure force is normal to the dam's wall, and the wall itself is at an angle, you have 2 components that this force has. The horizontal component, which is your Fx, and the vertical component, which is your Fy. These are these ones here. And since F goes through this point of center of pressure, the moment that is calculated about point A has 2 contributions. A contribution from Fx and Fy. And now, while Fx gives you a clockwise moment about point A that would contribute to the dam tipping over about point A, then Fy would in fact contribute against that. It would create a counterclockwise moment about point A. So it would press against the ground. So as you can see, this shape is more beneficial for the dam than this shape that we had in the previous dam exercise. This trapezoidal shape is more beneficial against letting the dam tip over about point A. And also, the greater the diagonal, the bigger the vertical component that fights against the dam tipping over about point A. Welcome back. Now what we also need to do is to find the center of gravity in the cross-section of the concrete dam itself, because force of gravity goes through that point. However, it is easier to do it later, once this minimum D is found. Since the dam is symmetric about the vertical axis and the density of the concrete in the dam is assumed to be constant, so it's 2.5 megagrams per cube meter, And we also assume that our gravitational acceleration g is constant, 9.81 meters per second squared. Because of that, Cg equals Cm equals the centroid. And we know that this centroid is somewhere here on this vertical axis in the middle of the cross section. Where exactly? That we can calculate later. But we don't need this specific point to compute the moment about point A due to force of gravity. That's because wherever the center of gravity is on this blue line, the moment arm from this vertical axis till point A, it's d over 2 meters. So the total width of the cross section is d meters, and this is d over 2 meters. And that doesn't change whether you are here or a bit above or a bit below. The moment arm is always d over 2 meters. So you would always get the same moment. To compute the force of gravity of the dam, we have Fg equals the mass of the dam times g. The mass of the dam is the density of the concrete times the volume of the dam times g. Since you know that the width of the dam is 8 meters, you can rewrite this volume like this. Rho c times, and now instead of volume, I will have the area of the cross section times 8, and now times g. To get the area of this cross section, you essentially need to calculate the area of this trapezoid. So first of all, the density of the concrete is 2,500 kilograms per cube meter, or 2.5 megagrams per cube meter. Then this one, it's the area of the trapezoid. D plus 1.5 divided by 2 times the height of the trapezoid, 9 meters. It's just a formula of a trapezoidal area. And now I will have times 8 here, and now I will have g here, and so you have 90,000 times d plus 1.5 times g, that's in newtons, and that's your force of gravity. And so you have your force due to water pressure and your force of gravity. And you know the center of pressure through which this force acts. It's at L over 3 meters along the wall from the bottom. And this is your L here. And just like in the previous dam exercise, to find the minimum D, the sum of all the moments due to these forces about point A must be 0 Newton meters. As you can see in this image, the moment arm for the force of gravity is d over 2 meters. Now, if this is our point A, then now we need to find the horizontal and vertical distances from the center of pressure till point A. So first, let's find this horizontal distance. Essentially, you have this distance, and then from point B, you have this distance here. And you know that in total you have d meters. Since you know this angle phi here, and you know that from point B till the center of pressure, you have L over 3 meters, you can form another right triangle here, where you have this horizontal distance and this vertical distance. To find this horizontal distance, you can have L over 3 times cosine phi. That will give you this horizontal distance. Now, what is cosine phi? If you look at this bigger right triangle here, so this entire right triangle here, where this is your phi, then you can say that cosine phi equals the adjacent side divided by the length of the dam. So d minus 1.5 over 2, and now if you divide it by L, then it's the same thing like multiplying it by 1 over L. So in the end, this is your cosine phi. And then we can also right away obtain sine phi, which is the opposite side of this right triangle over the hypotenuse. So it's 9 over L. Note that these are cosine phi and sine phi. With cosine alpha and sine alpha, it was in reverse because your alpha was this angle here. So cosine alpha was 9 over L and sine alpha was d minus 1.5 over 2 and all that divided by L. So with this phi angle, the values have switched. And now this horizontal distance, it's this one here. And now you know your cosine phi. So let me call this entire thing L horizontal 1. And so your L horizontal 1 equals L over 3. And instead of cosine phi, I will write this thing here. And as you can see, I can cancel out the L's. And I will have d minus 1.5 over 6. So that's this horizontal distance. And now let's calculate this L horizontal 2. Well, that's easy. L horizontal 2 equals d minus L horizontal 1. So it's d minus 1.5 over 6. And now we also need to calculate the vertical distance from the center of pressure till point A. Let's call it L vertical 1, and that's going to be L over 3 times sine phi. But you know what your sine phi is. It's 9 over L. So you will have L over 3 times 9 over L. You cancel out the L's, and you will have 3 meters. So that's the vertical distance from your center of pressure till point A. And now we can calculate the total moment sum about point A, and we can equate it to 0 newtons times meter. So I will have the moment sum about point A equals 0. And now remember, this one here, that's your Fx, and this one here, that's your Fy, the downward vertical force. And so the moment arm for Fx from point A, that's this one, 3 meters. So minus Fx times 3, that will give you a clockwise moment about point A. Then the moment arm for Fy, that's this one, LH2. So you will have plus Fy times LH2. That will give you a counterclockwise moment about point A, plus, and then you take your force of gravity that you have here and you multiply it by its moment arm, which is d over 2 meters. So Fg times d over 2. That's a counterclockwise moment about point A. And I will equate that to 0. You can see that the moment due to Fx, which would cause the dam to tip over, is countered by 2 other moments, one from Fy and one from Fg. And so when the moments balance each other out perfectly, then their sum is 0. And now what you need to do, you need to find this d. That's your unknown. That's when you have your d minimum, when the sum of all the moments is 0. And now, this Fx, you know that it's f times cosine alpha, and you know your cosine alpha, so Fx equals this f, which we can simplify by making this one 1 and this one 36,000. In other words, this is your force, L times 36,000 times g newtons. And so I'm gonna write it here. This is my force F times cosine alpha, so times 9 over L. You can cancel out the L's and you will have 324,000 times G newtons. And now Fy, that's minus F times sine alpha, so it's minus, then this is the force, and this is sine alpha, d minus 1.5 over 2L. Again, you can cancel out the L's, and you will be left with minus 18,000 times d minus 1.5 times g, and that's also in newtons. And now you can put your Fx and Fy into your moment equation, along with your Fg, which is 90,000 times d plus 1.5 times g. So the first term, it's this one, minus Fx times 3, it's this one here. Then the second term, it's this one here. And finally, the third term, which is this one, it's this one here. And all that equals 0. You can see that from all the terms, you can cancel out the g's. And then I need to take this equation and make mathematical manipulations with it. In other words, I need to open up the parentheses. So for example, this is our equation. What we can do here, we can write it in this form, or in other words, in this form. And then what we can do, we can put this expression here, and then you have 6 here. We can get rid of it if we have 3,000 instead of 18,000 here. Then we can take this section here, let's call it 1. I'm gonna rewrite it here. If I open up the parentheses, then I will have this expression, or in other words, this expression. And so what I can do now, I can take this term and I can say that it's minus 972,000. Then in this term, notice I have 2 here, which means that in here I can write 45,000. And so let me take this term, let me call it 2. I'm gonna rewrite it here again, and I can also rewrite it like this. So I can rewrite this entire equation now in this form. This first term, that's the second term here. Then here the second and the third term, it's this one here. And then this one here, it's this one here. If I manipulate this equation further, then I will have this equation here. And so what we have here is a quadratic equation that looks like this. Ax squared plus bx plus c equals 0. X here is d here. And so we have to find our d. For that we have to solve this quadratic equation. We have to find its roots. In this abstract equation, we have to solve for x. In order to solve for x, I will do the following. I will divide all terms by a. Here the a's get cancelled, and so I will have x squared plus b over a times x plus c over a equals 0. Then I will write it like this. X squared plus b over a times x equals minus c over a. And now what I will do, on both sides of the equation sign, I will add plus b over 2a squared, and here as well, plus b over 2a squared. You can do that because it's not going to change the equality of these equations. But the reason why I did that is because now this side can be written like this: x plus b over 2a squared. And this side can be written like this. So I have this thing on one side, this thing on another side, and now to get rid of this squared, I apply square root here, and I have to do the same thing here, but I also need to put here plus minus, because remember, 2 squared equals 4, and also minus 2 squared equals 4. So when you go back, square root of 4, then it's actually plus minus 2. And so you will have this thing here. In other words, you will have x equals this thing, or simply you have this expression here. And that's the quadratic formula to solve for x. So you can use it to solve for your d. So for this equation, I will have d equals, now this one is my a, this one is my b, and this one is my c. So I have minus b plus minus b squared minus 4 times a times c, and all that divided by 2 times a. And so because of this plus minus sign, you will have two solutions. d1 equals 3.65 meters, d2 equals minus 4.47 meters. Now one solution is negative, and you cannot have negative d, which means that the solution that is acceptable to you, it's this one, 3.65 meters. And there you go. Your d minimum is 3.65 meters. If your d is greater than or equal to 3.65 meters, then the dam won't go over about point A. But if d is less than 3.65 meters, then the pressure from water will turn the dam over. Welcome back. So we have found our minimum d, 3.65 meters. If d is less than this number, then this dam will tip over about point A due to the pressure from this water on the left side. However, we are not done yet. We still have to find the center of gravity of the concrete dam itself in this dam's cross-section. As mentioned before, since the density in the dam is assumed to be constant, 2.5 megagrams per cube meter, and we also assume that G is constant, which is 9.81 meters per second squared, because of that, we only need to find the area centroid of the cross-section of this dam. It will be the same like CM and CG. Now, normally you would find the area centroid through integration. However, here we can do it more easily. We can divide this cross-section into 3 parts, 2 right triangle parts and 1 rectangular part. The centroid for the rectangular part is easy. Due to symmetry, it's in the middle of the rectangle. Now let this point B here be the origin of the coordinate frame from which we measure our centroids. Let's call the centroid of the rectangle C2. You know that the total distance of the lower part of the dam is 3.65 meters. It means that this point, C2, measured from this point B, its coordinates are the following. C2x equals 3.65 over 2, so the total distance of the lower part of the dam divided by 2, and it's 1.825 meters. So it's this distance here. That's your C2x. And then C2y equals, the total height of the dam is 9 meters in the vertical direction, and so you would divide 9 by 2, and you would have 4.5 meters. So it's this one here. That's your C2y. And then you have two right triangles, one on the left, one on the right. You already know from the previous problems where the centroid lies in the right triangle. From this corner here, you go 1/3 of the total height of the dam up, and then 1/3 of this entire length to the left. And the same thing with the other right triangle. 1/3 of the total height up, and 1/3 of this entire distance to the right. So we can call this point C1 and this one C3. From the origin of this coordinate frame, from point B, we can measure C1x, C1y, also C3x, and C3y. In order to do that, we need to calculate this distance here, d minus 1.5 over 2. Well, that would simply be 3.65 minus 1.5 over 2. That would be 1.075 meters. That's this entire distance. And now, if this distance here is 1/3 of 1.075 meters, then this distance here, this green one, it's 2/3 of 1.075. And that would actually be 1.075 times 2 over 3, and that will give you 2.15 over 3 meters. It's this distance here, C1x. This distance here, that's 1.075 over 3 meters. And now you know that from the total height of the dam, vertically, C1 is at 1/3 of the height. So 9 over 3, that's 3 meters. So it's this one here, C1y. And in fact, it's also your C3y. That's also 9 over 3 equals 3 meters. And now we need to find C3x. So the horizontal distance from B till C3. Well, for that, you take this distance, which is 1.075 meters, plus this distance, which is 1.5 meters, and then finally, you add to that this distance, which is 1.075 over 3. So you have 1.075 plus 1.5 plus 1.075 over 3, and that will give you 8.8 over 3 meters. And now that we have these coordinates, we have to get a combined area centroid from these three sections. And we will do that in a similar way like we did with a trapezoidal force distribution, where we found its center of pressure by dividing this distribution into two parts. You can do a similar thing here. We first calculate the areas of the three sections of the dam. So let's call this area A1, then this one A2, and this one A3. A1 equals, now this side is 1.075 meters, then I multiply that by the height of the dam, and I divide it by 2, and in the end I will have 4.8375 meters squared, and that's my A1, and that's also my A3. And then A2 equals, this side is 1.5 meters, the height of the dam is 9 meters, so 1.5 times 9, that's 13.5 meters squared. And then we do the following. We take this area 1, and then we multiply it by C1x. That's the horizontal position of the centroid of the area corresponding to A1, measured from point B. You have A1, you have C1x. If you multiply them together, then you will have this number, which is meters squared times meters. In other words, it's meters cubed. Then I take A2, which is this rectangular area, and I multiply by its corresponding horizontal position of the centroid measured from point B. So C2x. If you multiply them together, then you will have this number here. And then I take A3, which is this area here. This area has a centroid, and I take a horizontal position of this centroid measured from point B. So A3 times C3x. That's 14.19 meters cubed. And now what I will do, I will sum up these three products. So A1 times C1x plus A2 times C2x plus A3 times C3x. And that will give me this number here. And then what I will do, I will add up all my three areas together. So I'm gonna have A1 plus A2 plus A3, and that's 23.175 meters squared. And let's call it area total. And let's call this sum of all these products MT. It's not a moment, I'm just calling it MT, M total. And now I have A total that I will multiply by my combined centroid of the entire cross-section in the x direction, and it has to equal M total. And so x bar C, that's MT over AT, and that will give me 1.825 meters. So x bar C, that's the combined centroid of the trapezoidal cross-section in the x direction, measured from point B. As expected, it's right in the middle of the cross-section. You can check it. This side here, this one, that's 1.075 meters, and then this side here, that's 1.5 over 2, so 0.75 meters. So 1.075 plus 0.75, well, that's 1.825 meters. So the math works out. And now to find y bar C, the centroid, in the y dimension for the entire trapezoidal cross-section, we follow the similar procedure. I will take area 1 and I will multiply it by C1y. C1y, that's the centroid of the area A1 in the y direction, measured from point B. It equals this one. Then I take A2 and I multiply it by C2y. That's this one. And then I take A3 times C3y, and it will be the same like A1 times C1y. This result here. Now we will take these three products, we will add them together, we will have 89.775 cube meters. We already know our area total. Now this sum of the products, with regards to the x dimension, we called it MT, but now let's rename it to MTX, because we're going to call this product MTY, this one here. And now, if I take my area total and multiply it by y bar C, which is the total vertical centroid of the entire trapezoidal area, that must give you MTY. And now y bar C equals MTY over AT, and that will give you 3.874 meters. And there you go. The general centroid of the entire trapezoidal cross-section measured from point B is the following. X bar C is this one here, and Y bar C is this one here. So the total combined centroid is somewhere here. Horizontally, it's in the middle of this trapezoidal cross-section, but vertically, it's in between C2 and the C1 and C3 points. Because remember, C2 was 4.5 meters, C1 and C3, they were 3 meters, and so it's logical that your total Y bar C is in between them, so it's 3.874 meters. And it's also the location of your center of mass and center of gravity. So the force of gravity as a point force acts through this very point, this one here. That's how you calculate the general centroid of composite bodies when it consists of multiple easier sections. You can avoid integration then. Thank you very much.